In our previous lesson, we were working with right triangles to find the length of missing sides, so the distance of a side. Today we're going to look at finding some distances on the coordinate plane. So for example, here in our number 1, we have our segment denoted here in red, and we'd like to find the distance. So you think about how the segment is, it's horizontal, right? It has a slope of 0. If we wanted to find its length, what could we do? Well, because it's a horizontal segment, I could count the number of units its length would be. So again, we're counting 1, 2, 3, 4 units in length from endpoint to endpoint. Let's take a look at the second example. Here we want to find the length of the segment in red again. What could we do? Well, if we notice in this one, our segment is a vertical line. Its slope is undefined. And we could find the distance between the endpoints by counting the number of units. So again, if we start here, we have 1, 2, 3, 4, 5, 6 units in length. Now if we take a look at our third example, again, we want to find the length of the segment in orange. What could we do? Well, if you notice, the segment in orange is not vertical, nor is it horizontal. We see how it's in between the endpoints of the green point and the black point. So we can't count the number of units in its length because, again, it's not vertical or horizontal. If we estimate here, we know it's definitely going to be more than 1 unit, probably more than 2 units, but we're not quite sure. Is there a way that we could calculate the length of that segment drawing on what we've done in the past? Well, in the past, we're used to working with right triangles. So we could form a right triangle using the orange segment as the hypotenuse. And so we're drawing in a vertical segment and a horizontal segment that we could find the values for. This vertical segment here has a length of 1. This horizontal segment here has a length of 2. So if we're thinking about our right triangles, our Pythagorean theorem says the sum of the 2 legs squared is equal to the hypotenuse squared. So 1 squared plus 2 squared is equal to the hypotenuse squared. In this case, I'll just use C to represent the hypotenuse, the orange segment that we had. Well, now we're just going to simplify and then undo our equation to solve for C. Well, 1 squared, that's 1. 2 squared is 4. And if I add them together, that gives me 5. So 5 equals C squared. I want to find the length of C, though. How do we undo something that's squared? We take the square root of each side. And again, remember the square root of C squared is the absolute value of C. And then we ask ourselves, is 5 a perfect square? Does it have any perfect square factors? If so, we're going to simplify. If not, we're going to leave as is. Well, 5 is not a perfect square, nor does it have any perfect square factors. So we're going to leave our distance here being the square root of 5. Now remember, absolute value measures the distance from 0. So if I was at 0 and I went to the left, I would have a negative square root of 5 units in length. We've talked about this before, how we're not allowed to have negative lengths for our figures, so we'd have to rule that one out. Again, if I started at 0 and went to the right, my distance, the square root of 5, that would be my length for my triangle, and I could use that for my length, and so that is what we would have for the orange segment that was here. So again, our length we calculated to be the square root of 5. Now, if you grabbed a calculator and you typed that in, that's a little bit more than 2.2 units in length. So if you were doing your estimating and you said it was a little bit more than 2, you're still on target. But now we've got the exact value and we know how to calculate lengths of non-vertical and non-horizontal segments. So let's look at this fifth scenario. Could you determine the length of the segment here in red? I could implement the same system that I did before if I draw the vertical and horizontal segments forming up the diagonal piece we'll call here. So I have a right triangle where I know one leg is 7 and the other leg is 6. So I can implement my Pythagorean theorem. 7 squared plus 6 squared is equal to that hypotenuse, which is the red segment, squared. Well, we know 7 squared is 49 and 6 squared is 36. If I add those together, I get 85. So if 85 is equal to the hypotenuse squared, could we just find the hypotenuse? Well, how do we undo something that's squared? We take the square root of each side. And so again, we'll have the absolute value of c equaling the square root of 85. We have to ask ourselves again, is 85 a perfect square, or does it have any perfect square factors? If so, we're going to continue simplifying. If not, we're going to leave it as is. 85 is not a perfect square, nor does it have any perfect square factors. So again, if we think about the distance we're traveling from 0, if I go to the left, that distance, that would be a negative square root of 85. And if I went to the right, that distance, it would be a positive square root of 85. Lengths, distances can only be positive measurements, so I have to eliminate the negative square root of 85 from my possible answer, and I would just have the square root of 85 for the length of my segment. Let's try another. Number 6, could you determine the length of the segment in red? If I draw the vertical and horizontal segments that are making up that diagonal distance, we have a length of 1 and 9, and those represent the legs of the right triangle. The red segment is the hypotenuse. So using our Pythagorean theorem, we know that the sum of the legs squared is equal to the hypotenuse squared. Therefore, 1 squared plus 9 squared is equal to c squared, c representing your hypotenuse. Well, 1 squared is 1, 9 squared is 81. If we add those together, I now have 82. 82 is equivalent to c squared. I want to undo that to solve for c, the hypotenuse. So how do you undo something that's squared? You take the square root of each side. So we know this is going to give us the absolute value of c. Again, we're going to pause and ask ourselves, is 82 a perfect square, or does it have any perfect square factors? If so, we're going to continue simplifying. 82 is not a perfect square, nor does it have any perfect square factors, so we're going to leave it as is. And again, we're thinking about going to the left and right, our distance of 0. If we went to the left of 0, we would have a length of a negative square root of 82. And if we go to the right, we would have a positive square root of 82. Again, our lengths can only be positive, so we have to eliminate that negative result. And so we have the square root of 82 for the length of our distance here in red. So we've seen how we can create right triangles to help calculate the length of a segment that's not vertical nor horizontal. Do you think there's a way we could find a pattern that would help us find this length if we had variables instead of numbers? And perhaps this equation or this pattern that we come up with would help us in the future not to have to draw right triangles to calculate your values. So if we think about the approach that we did, if we were making right triangles, we were drawing a vertical and a horizontal segment. And we were then figuring out the distances, the lengths of each of those segments. So if I wanted to find the length of this vertical segment here, and let me change that to blue. How could I find that? Well, vertical, that's your y direction, right? So if I knew this y value here, b, and I knew the y value here, well, that would happen to be d, I can figure out that length. Well, if I took b minus d, I would have that result. Then we worked on finding the length of the horizontal segment. Well, those are your x coordinates. That's your a, and that's also c. And if we took the difference of those, that gave us the length here. So now we have the lengths of the vertical and the horizontal segments. We can use that to find the hypotenuse just like we did before. The sum of the two legs squared is equal to your hypotenuse squared. Since we're talking about that length, I'm just going to call it length right now for the hypotenuse. Now typically these were values, so we squared them, we added them together, and ultimately to get the length by itself, since it was squared, we took the square root of each side. So if we think about taking the square root of each side, we'd have the square root of this value, and this would be the absolute value of the length. And we know that lengths are always positive, so we were always ruling out that one negative result. So at this point, we've generalized now a way of finding the length of the segment based on the coordinates of the endpoints. So we don't necessarily have to draw the right triangles anymore and calculate the individual lengths. If I know the coordinates of the endpoints, I could put them into this pattern and simplify that expression, and I'll have the lengths. Well, this is how the distance formula was derived. It was based on using the Pythagorean Theorem to use the endpoints of the segment to calculate that length. So oftentimes you see the distance formula represented by d, that was the length of your hypotenuse, equals the square root of the difference of the x's, that was the length of your horizontal segment, plus the differences of the y's, that was the length of the vertical segment of your triangle, and you take the square root of that, and then you're all set. Again, it's just a rearrangement of your Pythagorean theorem, right? This is what we typically started with, and then when we undid the Pythagorean theorem to solve for C, this is what we ended up with. So again, we were just replacing the lengths of A and B with the coordinates with how we were calculating them. And so as long as we know the coordinates, we can just substitute it into our formula and have our lengths fairly quickly. This is nice because we don't know exactly where things are located on the coordinate plane. We don't know what kind of scales we'd have on the coordinate plane. So drawing right triangles and using the Pythagorean theorem is not always feasible. This comes in handy. So let's try a couple using your distance formula, find the lengths of your segments. So if you take a look at number 9, we want to calculate the distance between the points of -2, 3 and -7, -7. So if it helps you envision your segment, this is the length that we're looking for, the distance between the two endpoints. So again, thinking about your distance formula, the distance is calculated from the difference of the x's. So let's say we're going to start at this point. Our x value is -7. So I would take -7 minus -2 squared, and I would add that to the difference of the y's. Since I started at this endpoint, I have to go back to that endpoint for the y values, -7 minus 3, and square that. Now remember, anytime you're subtracting a negative, it's saying, hey, take the opposite, so that's really an addition problem. So here we're going to think about -7 plus 2, well, that would be -5, and we would square that. -7 minus 3, well, that would be -10, and we would have to square that. Well, a negative times a negative is a positive. -5 times -5, that's going to be 25. -10 times -10, that's 100. And we add them together and we get 125. Again, anytime that you have a radical, you've got to ask yourself, is it a perfect square? Does it have any perfect square factors? 125, we can see 25 here. That's the perfect square factor. In fact, 25 times 5 is what gives you 125. So we know the square root of 25 is 5. So our exact length of our segment is 5 square root of 5 units. Let's have you try number 10 here. Again, could you calculate the distance between the points given? You have one point at -1, 4, and the other point at 2, -9. So again, if it helps you envision it, you can draw it in, and then just decide where you want to start. So let's say I start here at the end point. I'm going to do the difference of the x's. -1 minus 2 squared plus 4 minus -9 squared. And again, that's all underneath the radical. Again, anytime that you see subtracting a negative, it's saying take the opposite, so we would be adding a positive. Now we're going to simplify each of those parentheses. -1 minus 2, that would be -3 we'd have to square. 4 plus 9, that would be a 13 we'd have to square. Well, -3 times -3 is 9. 13 times 13, that's 169. If we add those together, we get 178. So again, we have to think about, is the square root of 178 a perfect square, or does it have any perfect square factors? If so, we're going to simplify it just like we did in the last problem. If not, we're going to leave it as is, and we have the exact length for our segment between the two given points. 178 is not a perfect square. It does not have any perfect square factors, so we've correctly calculated the length of our segment.